So the statement is written here. Suppose that P and Q are some polynomials, co-prime, and suppose that there are 4 distinct linear combinations that are perfect squares in this in the field K of T. Then necessarily the P and Q are constants. So 4 distinct linear combinations means A1P plus B1Q, etc. With A1, AI, BI in P1 distinct points. So I'm going to say, given 4 points in P1K by a linear change of variables, a linear change of coordinates, I can assume they are one, 0, 0, 1, 1, 1, and 1 lambda, with lambda not equal to. Okay, so this is just a trivial little trick. P1K is K2 minus the origin divided out by similarity, and so the first two guys I take to be a basis. Take the first two as a basis of K2. And then the third one, well, it's supposed to be distinct from both of those, so it's got 2 non-zero coefficients there. And so if I just scale up, I take the first guy, which was a basis, I multiply them through by a little bit, and then I multiply the second one through by a little bit, I can arrange these scalars to be 1, 1. Scale them to make the second to be 1, 1. And then the third one has to be something, and it has to be something with non-zero coefficients in both, because otherwise he'd be equal to one of those, and so he's got to be of this form. So this argument is used again and again in projective geometry. So it says roughly 4 points are 0, 1, infinity, and lambda. And the lambda is a cross ratio. The lambda then can't be changed. Lambda is the cross ratio. So I start off with P and Q, 2 polynomials, and I assume they're co-prime. I assume that 4 distinct linear combinations are perfect squares. And then the conclusion is they're constants. So how am I going to prove this? So the idea, so first of all, I can replace K by K, the algebraic closure. of k. So this is completely harmless. If I've got P and Q, if I've got P and Q in K, then in particular P and Q are in the bigger field K, and if four linear combinations of them are perfect squares in little k, they're certainly perfect squares in big K, in polynomial ring over big K, and if they don't exist in big K, then they certainly don't exist in little k. Right, so there's no, this is completely harmless. Right, but I want it in order to be able to take square roots of these quantities that turn up. So assume that P is a perfect square, and this means that P is U squared, and Q is V squared. U and V are still in K of T. Right, and so this is the argument here, I mean, it's called infinite descent. So this is, Fermat had this idea of infinite descent. So we're trying to prove that P and Q don't exist. And so I can go down to U and V. I claim that U and V also satisfy the same assumption as P and Q. Right, so namely I claim that they're two co-prime elements and that four linear combinations of them are perfect squares. So I'll come back to that in just a minute. But the point is that the degree of U and the degree of V as a pair are less than, strictly less than, the degree of P and the degree of Q. So I can say that the max degree P, degree Q is greater than the max of the degree U and the degree V. So, you know, this is a sort of, there are two logical things going on. I'm arguing by contradiction, so assume that P and Q exist and are not constant, then if they're not constant, they have positive degree. And at the same time, I'm arguing by lowering the degree, so it's really an argument by induction on the degree. Right? So, if these two guys exist and have degree positive, then I can make new guys, U and V, which still exist and still have positive degree, but positive degree strictly smaller. And so, you know, the degree is an integer. It starts off being something non-zero, and something positive, and it decreases. It can't decrease forever. So at the end we get a contradiction. Right? So this method is used in number theory. It's used whenever you talk about you know, these proofs of things like Mordell-Weil theorem on elliptic curves, or any results about the arithmetic of elliptic curves. You use this kind of method. So this is infinite descent. So, you know, it's not, strictly speaking, proof by induction. Because it's a proof by induction and contradiction at the same time. Okay? So anyway, so I need this. So anyway, at the end, this is a contradiction. So I hope the contradiction is clear. If these guys exist and are not constant, and they have some positive degree, and then U and V are going to be the same, going to have exactly the same assumptions, but have a strictly smaller degree. And so at the end, you know, these two guys don't exist, or these two guys are constants, and that contradicts that P and Q are not constants. Okay, so what am I going to say about U and V? Well, the thing I've got is that so P is U squared and Q is V squared. So I've sort of, I'm cashing in, I'm making use of the assumption here, right? But I've got two other linear combinations, also U squared minus V squared and U squared minus lambda V squared are linear combinations, are perfect squares. Right, so you know, I can change this to 1 minus 1 and 1 minus lambda here. It doesn't make the slightest difference. Right? So this is U minus V into U plus V, and this one is U minus mu V U plus mu V, where mu is the square root of lambda. So this is actually the only place where I use algebraically closed. Yeah? So let's think about any one of these four terms. So U and V are coprime. They're coprime because P and Q are coprime. And so therefore, so also U minus V and U plus V are coprime. So these are polynomials. They're polynomials of some degree. If there was a common factor here, then there'd be a common factor. If there was a common factor here, then there'd be a common factor here, because I can get U and V just as linear combinations of these two. Right. On the other hand, U minus V times U plus V is a perfect square. Right, so this is, some, we had earlier all these P squareds and Q squareds and so on. So this is some F squared, F polynomial. Okay, but now exactly the same argument we had before. If I have an irreducible factor inside this F, then he's got to divide one of these two. And moreover, he can't divide both of them because they're coprime. And so therefore, any factor in this F, well, the square of it is in F squared, and that means the square of it is in one of these two. So when you think about breaking this up into as a product of primes, then the F is a product of irreducible polynomials, and the F squared is a product of irreducible polynomials, each of them to even powers. And so each of these, the only way that all the terms on the right-hand side appear as even combinations, as even powers, and so an even power of them divides one of these two. Therefore, so U minus V and U plus V are perfect squares. So it's simple. It's sort of just quite a long argument. So, right, and then the same way, similarly, U minus mu V and u minus plus uv are also perfect squares. So, you know, the combinations here are, these are the points 1 minus 1, 1 plus 1, 1 minus 1, 1 minus mu, 1 plus mu, 1 minus mu. And these are still 4 distinct linear combinations of uv are perfect squares. So this is a contradiction. If they existed, then there would be some element there which is the smallest, has the smallest degree, smallest positive degree of u and v. And if there was a small, if I have any one, I can always find a smaller one, and that's a contradiction. There can't be a smallest one. Okay, so this is a sort of basically strange argument. You know, it's nothing very difficult about it, but it's a sort of slightly bizarre argument. It's a slightly strange argument. I hope we have some white chalk. So, so the conclusion. Let me sort of look forward to things that we're going to be doing later. The conclusion is that non-singular C3 in P2 is not rational. So later on there'll be this thing called a genus of a curve. And we'll have that P1C has genus 0, and this C3 in P2 has genus 1. So genus 0 means as a topological space it looks like this, as a Riemann surface, as a algebraic curve over the complex numbers. It has real locus looking like this, and here this one has genus 1, meaning it's like this. And so you know, I've done this argument here using these funny kind of number theory stuff, the stuff that looks exactly like number theory but in a polynomial ring, and we come to the conclusion that that the curve, that these two guys are not isomorphic. Right? And, you know, if you're a geometer, you say, well, nothing very surprising about it. Of course they're not isomorphic. However, establishing what this genus is and why this is true is something that's going to take a long time. Okay, so I'm going to go to the next topic about non-singular elliptic curves, non-singular curves in the plane. Namely, I'm going to say that they have a group law. So they have an additive group law, and abelian, they're abelian varieties. So this is also something where there is one of these proofs. I'm going to give a proof. I'm going to give most of a proof, and it's slightly strange. You know, it's so I explained last time. I can do this construction if I've got 2 points P and Q. I can make a third point R. So this is, so let me call this point R P star Q. Right, so PQ maps to P star Q is a kind of binary operation on points of C. So I'm thinking of points of C over K. Okay, and I want to one thing. I want to notice that this is defined without exception. So a binary operation is supposed to be a map from C cross C into C. So I've drawn a nice little picture there. It tells you what it is. However, it tells you what it is, assuming that P, Q, and R are distinct. So, in other words, I assert that this makes sense even if P, Q, R are not distinct. So it might happen, so, you know, for example, it might happen that P and Q are the same point. You know, when you define a group law, you can't say, oh well, I'm going to define G1 times G2 in this way, except that I'm not going to bother if some coincidence happens. So let me draw this picture there. If P equals Q, so e.g. if P equals Q, I take the line of P2 such that I take the line L of P2 such that L intersects C is 2P plus R for some P. Sorry, for some R. Right? So, I've told you what this means. Right? For any line L in P2, L intersects C is points with multiplicity. Right? Because, you know, this just corresponds to P1 of UV, and my trick in this chapter is always to think of the equation of C restricted down to give a homogeneous cubic polynomial in U and V. Right? So this L intersects C, it's not really a geometric picture, it's really this algebraic thing of having a cubic form in two variables. So the assertion is, if I've got P and C, there exists a unique line L, such that L intersects C has a multiple root at P, has a double root at least a double root at P. Yes. So this is what it means for a curve to be non-singular. The line. I'll come back to this later in the course to do it more formally, but so this assumption here the thing I've just called star is the same, is the assumption that C is non-singular. So non-singular means, you know, I don't know. Let me not worry too much about this. You have this picture. Exactly, this picture is very familiar from where you talk about the tangent line to a curve when you're defining the when you define the derivative of a function. So you know, if I do something like that, then what's the tangent line at this point? Well, every line through the point has a double, and also there's no well-defined tangent line. So so let me just leave this for the moment. So so to define 2p, I use this tangent line PL instead of line PQ. Right? And it can happen that L meets C at, you know, for example, 2p plus q, or 3p, in which case, so if this is 2p plus q, then I'm saying p star p, I'm saying that p star q equals p. So there's nothing, that's allowed. Right, p, this is saying that p star p is p again. Right? But it's always defined. It's defined just because I've told you what I'm going to do when p is not equal to q. When p is not equal to q, I take this line, I factorize the cubic polynomial restricted to the line as this factor times some third factor. So R is the third point of intersection of L with C, where L is PQ, or the tangent line to P at C. Right, and that's always well defined. Okay, now what do I want to do? So where's the group law? So you know, if you cast your mind back to when, if you remember when you were first introduced to the idea of a group G has a multiplication law, G cross G, and it also has a unit element, E in G. Right? And the problem with what I'm saying, the problem with trying to make this into a group law is that where's the unit element? So we must specify some point O in C to be the unit element of the group. Right. So you know, there's no naturally. This is just a curve in the plane, and you know, it doesn't necessarily have a naturally occurring choice of points. So there are two stages in this, and my preference is to say in the first stage we just let O be any point. So first stage, let O in C be any point. So, you know, if we were over a non-algebraically closed field, I'd better assume that C has at least one point. So I'm assuming that C has a point over, defined over K. This is definitely an issue. This is not something simple that will go away. It can happen that it doesn't have a point. Okay, so what am I going to do then? Well, then the definition of the group law is to do this. I'm going to do P star Q, and then I'm going to do this star O. Is P plus Q. That's just the definition. Okay, so let me sort of draw a slightly more elaborate picture now. So here's P and Q. Here's this third point, P star Q. Right? And let's suppose that the origin O is there. So I join this up like that. So later on, this point here will just be minus of this point. At the moment, it's not quite that. Anyway, this is P plus Q. Okay, so here again, it's important that whatever this point, you know, these 2 points are just 2 points on the curve, any 2 points, they could coincide, and then this is the third point of intersection. So I always need that this is defined without exception. Okay, so there's proof, or partial proof, that this is a group law. So, okay, maybe I put proof in inverted commas because I'm going to miss out one little step. So what do we have to prove? So let's start with proving that P plus O is P. Right? So this element O really is the unit element. So what does it mean? So here it just means this. So here's my curve. Here's my P. Here's my O. So in this picture, what I'm doing is I'm constructing P star O here. Right? This is the intermediate stage. And then in order to construct this, the thing which is the target P plus Q, I've got to join this back up to O and take the third point of intersection. So that's easy. I join this one back up with this point. I draw the line. I take the third point of intersection. Right? So from P and O, go to P star O by the line PO. So the P star O is the third point of intersection of this line here, PO, with the curve. and then construct the line from P star O, so the line joining these 2 points, and take the third point. Yeah, so this is a complicated way of doing absolutely nothing. I'm going from P and O, constructing this third point, and I'm going from this third point and O, and I'm constructing the third point of intersection, which is just P again. Right, so I'm sort of batting forwards, and then I'm just batting backwards, and I get back, this is the identity map. So I'll explain why this is bizarre a little bit later. Later in the course I will give a treatment of this that doesn't involve any of these funny constructions of lines. And then you'll see that it's really not very geometric, but much more rigorous, much closer to simple, rigorous stuff. Okay, so what about minus P? Well, this gets sort of a little bit more strange with each step. So what we're going to do is this. Here is the point O. So I want to construct this point, this third point, O bar. So define O bar as O star O. So this star, as I said, is a binary relation. It's definitely not the multiplication in the group. So now, what I want to do is, I want that P plus P bar, of course I want P plus minus P to be 0. This is I want. Right? So I want that when I'm doing this construction of P plus minus P, so this is just some other point which I don't yet know, right? So I want to find another point there with the property that when I join this point and take the third point of intersection, I get some point such that when I join it to O and take it back, I get O again. So in other words, we want minus P to be a point such that to be a point x, unknown point x, such that P plus the P star x, so the third point of intersection of the line Px, joined up with O is O. So the solution to this is this. So this is x. So in other words, so here's how to solve this problem. So first of all I constructed this 0 bar. Right, so given C and 0 bar, define minus P by minus P equals P star 0 bar. Right, so in other words, I'm thinking of, let's pretend every line in the plane meets the curve in exactly 3 points. Right, then if I stand at this point and I look at the curve, I look out, I see 2 different images. I just look in that direction and there are 2 points there. There's one there and one there. And so let's interchange these 2 points. So that is the minus in the group law. Interchanges. The 2 points, or pairs of points. With P, X, O bar, collinear. Okay, so now, so let's prove that it works. So what is P plus minus P? So this means that I'm going to, it means that I'm going to do P plus this X I've just constructed, sorry, star X, right? And then, so this means I've taken the point P and the point X carefully constructed in this way and take the third point of intersection. So this is O bar. And then I'm going to do O bar star O, and then take, so that means I'm joining O bar to O and taking the third point of intersection of that line. And so this is the tangency at O. Right? So P plus minus P equals this equals O. Okay, so it's you know, it's a little bit strange, but the thing that makes it strange is that I tell you PQ goes to P plus Q, goes to P star Q, and you sort of possibly think that maybe that P star Q is itself the group law, and that's not the case. Then if the group law is the group law has the group. So the group law has the property that P plus Q plus R is constant for all lines L, with L intersects C equals P plus Q plus R. Right. So in other words, when I draw a straight line and I get 3 points, I think of this R as being something like minus P plus Q, and then it's been shifted around a bit. It's been shifted around by, you know, this O bar or something. Okay, so there's a big problem here, commutativity. And later on in the course, I'll tell you that you really don't have to do this, that it follows very simply from the fact that C is not rational. But I'd have to give a little argument here for it. So let me postpone this. Let me deal with this just a little bit later. Right, so I'll do it today, but I'll do it later today. So I told you this is the first stage. And what I'm using, if you think about the argument I've just given, what I use is that every line of space, every line of the plane, that already has 2 points of intersection with the curve, has a third point of intersection. Right? And I also use the fact that given any point, there's a unique line having this point as a double root. Right? So I need this P plus Q. I need this every line that meets C in 2 points meets it in a third. I need that in order for this operation PQ goes to P star Q to be defined. And then I also need this uniqueness of a tangent line at a point in order that I can make I can make the operation star there to be defined without exception, defined without any nasty singularities. Okay, so but let me give you the second stage, because the second stage is really much prettier. Second stage. So suppose that O is an inflection point. So the thing you notice, what's good about being an inflection point? Well, just think about this. All of this constructing the minus involved this point O bar, right? And the group law there, as I say, it has the property that P plus Q plus R is a constant, and the constant is 2O plus O bar or something like this. So if the origin were chosen to be an inflection line, a point of inflection, then when I draw the tangent line, it meets the curve in 3 points, namely in this point with multiplicity 3. So the good thing about inflection points is immediately you get that O bar is equal to O. So inflection point, therefore O bar equals O. Right, moreover, I can write C in this form. I can write C is this y squared z equals x cubed plus ax z squared plus z cubed, bz cubed, right? So given an inflection point, I have this special form, this normal form, like this, right? And with O equals the point 0, 1, 0. So this is especially nice because the way you want to think of this as being the point at infinity in the direction of the y-axis. So this is the point y equals infinity. So then the straight lines passing through O, this is the lines passing through the lines, so O bar is equal to O. Moreover, I can choose the coordinates like this, so that this point O, which is the same as O bar, is the point at infinity. Then these lines here, in the picture, the lines are just the vertical lines. Right, so the group law becomes, just much simpler immediately. Then the group law. Then the second part of the construction of the group law so this is lines through O bar just amount to y goes to minus y. Okay, so when we write this curve y squared z equals x cubed plus ax z squared plus b z cubed. Right, so this is in P2. And you notice that the only place that y appears in this equation is in this term y squared. So if I go y to minus y, I don't change anything. So what I'm doing here is I'm taking a point like this. I'm taking a point x minus y, I'm taking a point xy1 in the affine piece with z not 0, and I'm just taking this down to x comma minus y1. Right, and this straight line here, this straight line is a vertical line, and so it passes through this line, vertical line, through P, passes through 0, 1, 0. So this is O equals O bar equals. So in other words, the proof, the group law has now come down to a thing that you can calculate quite easily and conveniently. So it's just this, P, Q, P star Q, and then this point here, where this is just x, y, goes to x minus y. Okay, so as I said, this is the theory of elliptic curves. Curves of genus 1 with a marked curve, a curve of genus 1 with a fixed point to be the group of the origin of the group. A plane cubic with a fixed point, fixed inflection point is called an elliptic curve. And so these are, if the field K is Q, or a number field, these are of great interest to number theorists. A whole lot of number theory is concerned with this. And the number theorists just use this picture. They don't have to worry about all the geometry or any of this tangent line stuff. Right? They just do this. So this is elliptic curve y squared equals x cubed plus ax plus b with the single point up to Pn for cubic, homogeneous cubics in x, y, z, such that so let me call the forms D, such that D of Pi equals 0. Okay, so I spent a little bit of time last time talking about the same construction with conics. So the thing I'm doing here is, here's a couple of points, and I'm looking at all the curves through there, and they're allowed to move around in a family. Right, they're moving. So this is a vector space. A vector space called a linear system of cubics. So if there are no p's, so S3 itself, S3 is this guy I had earlier on the blackboard, x cubed, x squared y, and so on, y cubed to z cubed. I was describing it as a Newton polygon. Did anybody take the trouble to count the number of elements in this? How many homogeneous monomials are there of degree 3? How many of them are there? Sorry? Okay, 10. So the general formula, there's a general formula which is, I'm just remembering, this is degree 3 in P2, so it's 5 choose 3. So 5 choose 2, it's 5 times 4 over 2 is 10. Right, so if it was degree 7 in P5, then you'd do a similar calculation, but quite a lot bigger number. So in other words, these the number of monomials in a pile like this is always a binomial coefficient. So what's the dimension we expect for this vector space? We expect, this is, we start with a 10-dimensional vector space, and we impose n linear conditions. So we expect the dimension to be 10 minus n. Okay, so the little thing I'm going to ask you to believe is that if I have P1 up to P8 in P2, and we assume that no 4 are collinear, and no 7 are anaconic. Then S3 of P1 up to P8 has dimension 2. Right. So you know the proof is in the textbook. I'm sure most of you know will have stumbled on it at some point. So this is proposition 2.6. And you know, the proof is just made up of the same ingredients as I spoke about last time. So the proof is nothing really new, and I certainly can't give a different proof of it from what's in the book. However, I want to say the following. This has a sort of quite nice corollary. So suppose that C1 and C2 are two cubics. Possibly singular, possibly anything they like, such that C1 intersects C2 equals P1 up to P9 distinct points. Right, so suppose that I've got this sort of ideal situation. Maybe I've got something like this. Here's one cubic curve. Here is another one. Let me draw. Right, and so if I draw a picture like this, then I've got 9 points of intersection. So suppose the only thing I'm assuming here is that these are distinct. Right, then if D is a cubic, is any cubic through P1 up to P8, then also P9 is in D. So I'm talking here about the geometry of P2. And so, different branches of mathematics relate to each other. You could get this result also out by different algebraic geometry. Later in the course I'll show you how to get it out of Riemann-Roch for curves, but it also follows from Cauchy's theorem in complex analysis. So I'm giving you a kind of little artificial proof that's actually quite pretty. So if I have some other cubic curve here that's passing through 8 of these points, then it is obliged to pass through the 9th point. Right? There is absolutely nothing like this in the case of conics. If I have a conic passing through 4 points, if I have conics passing through 4 points, they move in a linear system. So if I have a conic, if I have 5 points, then I've already fixed the conic, and there's no question. So this is the first time. The cubic curves are the first time you get really non-trivial geometric phenomenon. So this is to do with the fact that curves in the plane are curves of genus 1. They're not rational curves. And it's this is a reflection of many things, many different things in mathematics. But at the moment, I'm just giving it as a sort of corollary of these basically stupid manipulations of if a curve vanishes on more than 4 points on a line, then it contains the line, and so on and so forth. So let me just write this. This is a subtle point, and it's but proved by easy steps. Right, and so I don't know. People want to hear the rest of the proof of commutativity, or should I give it next time? I mean, the proof of commutativity, associativity. The proof that the group law on C is commutative is this figure on page 34 of UAG. So in other words, if I've got A, B, and C, then I can try to calculate A plus B first, and then C, or I can calculate B plus C first, and then calculate A plus B plus C. Right, so an associativity should mean that these two guys are equal. So we want these to be equal. Right, so this is a point. Okay, see, that's not so good, is it? This is a point on the curve, and this is another point on the curve. Right, so that funny picture on page, maybe I'll come back to it next time because everybody's tired. So there's a picture here. I can draw lots and lots of these lines, you know, something like this. Then I choose 3 of the lines like this to be one of this quadrant, one of this C1, another of the lines to be the other of the C2, P1 up to P8 are 8 of the points in the picture, and then the remaining cubic, namely C, has to pass through the 9th point. And that's the proof of this. So let me say it more slowly at the beginning of next time. Okay? Anyway, I mean, you know, the proof is quite pretty. It's quite, it is not especially informative. It doesn't tell you the whole truth. It just tells you a little bit of, you know, here is a funny statement and here is a funny proof.